Hi, everyone. My name is Roman. I work at a company called Sentry.io, where we build error and performance monitoring. And today I want to talk about bytecode transformations in the world of Android. But before we dive into the bytecode waters, I just want to expand a little bit on the topic of error monitoring. So imagine we have a simple app, a gallery app, where you can navigate through the pictures, when you can open a picture to see it zoomed in, and also you have some crashes, of course, in your app. Let's assume you are using some cloud solution to report these errors too, so you can monitor them in real time. Let's also assume your app is using Timber for logging, which is also pretty common nowadays, I think, for the Android apps. And you're using it in the following way. So you have some dangerous method that can crash, and you're using Timber to log a warning before entering this method. So you can capture the app state and know what's going on. Ideally, you would also want to send this log message to your error monitoring solution, so you can actually enrich the error events and see what's going on, and it would help you debugging the issue. With Timber, it's pretty straightforward to do. You can just create this custom crash reporting tree, check the log level. If it's a warning, you would use your crash library to report the warning. And then you would plan this tree for the release builds. I think it's a pretty standard setup for most of the Android apps, I think. Next up, let's assume we also use Glide for our sample app to load the images. Glide, in turn, uses Android logs inside, and you can specify here the minimum log level for reporting the logs. And somewhere later in Glide, they would call something like this, like log debug with some tag and some message. But what if you want this message also to end up in your very same error monitoring solution? Wouldn't this be great? And I think it would help you a lot to debug issues with your image loading and stuff like that. So is it possible to do? One straightforward way would be you just pulled in the Glide dependency locally. You would modify all the log calls to Timber logs. And since we set up this crash reporting tree, you would just, so it would work automatically, since you would change the log calls to Timber. But this is not really scalable, right? Because you're probably using a lot of different libraries, and it's not feasible to do this for all of them. So is there like an automated way to do this? Is there a way to transform the logd into timber.tag.t? Sounds like a problem for some metaprogramming approach. There are multiple ones on Android available. Let's go one by one. So the first one would be bytecode manipulation. It allows us to modify or add the JVM bytecode. The next one would be the Kotlin compiler plugin. So it also allows us to modify or add the Kotlin intermediate representation, and it also works for Kotlin multi-platform. Another one can be Kotlin or Java Poet. It allows to generate Kotlin and Java source code. And the last one is the brand new KSP, which allows to generate Kotlin symbols and also works for Kotlin multi-platform. I tried to put like 4 main areas that we need to look at. So whether the metaprogramming approach allows us to add new sources versus modifying them, and whether it works for project-only sources or whether it works also for dependencies. And if we put this into a table, we can basically identify what solution do we need here. So for the first cell here, if we want to add new code to the project files, basically all of the mentioned solutions would work here, because like KSP and Kotlin Poet, that's essentially their point to generate like new source code and then add attached to your application. And you can also do this with Kotlin compiler plugin or bytecode manipulation if you're feeling adventurous, because it's going to be a really complicated task. Next up, let's look at if we want to modify some project classes. Here we would only have two approaches, either a Kotlin compiler plugin or bytecode manipulation, because KSP and Kotlin Poet, they're designed to kind of be read-only, so they cannot modify already compiled classes. They can only add new classes. The next cell, adding new classes to dependencies. This is only possible with bytecode manipulation because Kotlin compiler plugins do not work for already compiled jars. And if you want to modify the dependencies again, this is only bytecode manipulation. So looking at this and reminding us about our goal, we want to modify the glide dependency. The solution here would be to use bytecode manipulation. What are the approaches of bytecode manipulation available on Android? So for years, there has been a so-called thing like Transform API. What is a Transform API? It's basically part of the Android Gradle plugin API. It allows us to process intermediary build artifacts, such as jars, classes, or resources. AGP would create a Gradle task for each such transform, and AGP would also handle dependencies between multiple transforms. So let's remind ourselves about how the build process looks on Android. So at first you have some Java or Kotlin sources. Then you would put them into the Java C or Kotlin C to compile them. This would produce classes or jars. Then these classes and jars would be put into some text tool, which is D8 nowadays. And finally, the DEX files will be packaged into the APK or AAB if you're using bundles. There is a nice talk at DroidCon 2019 from Doug Stevenson. Go check it out, about Transform APIs. So where exactly the Transform API kicks in? So it's actually happening here when you have compiled classes and jars, but before they are processed by D8. And as I mentioned, there can be a chain of transforms. So if you have multiple transforms, they will be run like that. And the array transform will be run last, because basically to make sure that your transform receives unminified and unobfuscated inputs. Otherwise, it would be a mess to instrument this bytecode. Let's take a look at the code. So if we were to write the timber transform, we would just give it a name, pretty straightforward. Then we would need to define the input types. In our case, we're interested in classes. As we said, we want to instrument the jar dependencies, so we would put external libraries here, the scopes. Then we would need to define if the transform is incremental or not. And finally, there is a transform function which we need to implement where the actual processing of classes and jar files is happening. This transform method can be a huge mess. There is a lot of boilerplate, around 200 lines, I think. And it's also repeating all the time. So if you open GitHub and search for usages of this Transform API, there will be like repeating code all the time. So basically, I guess it was copy-pasted once for all usages. There is a lot of boilerplate, but what we actually need is just this, right? So we just want to modify the inputs, want to modify the classes. So can this be hidden? Can this be done once and for all? So I think this was one of the reasons why the Transform API was deprecated in AGP 7. But there are other reasons as well, so let's go through them one by one. The first one is each such transform would create a new Gradle task. So if you're using like 3 Gradle plugins that are doing transforms, it would mean you have 3 new Gradle tasks, which would do the same thing. So they would all go through the classes and jars again and again, and this would slow down your build significantly. Next problem is there is a lot of boilerplate, as I mentioned, so you need to read the class bytes, and you need to modify them and write back for each class. You would also need to handle jar inputs and repeat the above thing, so open the jar, again, read the class bytes and modify them, write back, close the jar. You would also need to handle incremental transforms. And the last thing, you would also need to handle output folders properly in order to not break the chain, because if there are multiple transforms, you cannot mess up the outputs, right? Because the next transform is expecting you to give proper inputs. So the API is now deprecated, but moreover, it's also scheduled for removal in AGP version 8, which is going to happen somewhere later this year, I think. So if you're using this API, you should look for alternatives. But what are the alternatives? So there is no single replacement for this, but the closest one is the new instrumentation API, which is available from AGP 4.2. It has a lot of advantages compared to the old transform API. The first one is it has just a single Gradle task for all transforms. So it just processes the the classes from your project only in a single Gradle task. There is no repeating work, so reading input classes, jars, bytes, writing output, handling incremental builds, everything is done for you by AGP. It's better cacheable because it utilizes the Gradle's artifact transforms to process dependency jars, but we'll cover this later. And it has a very lightweight API. We'll see this later as well, but it just contains 2 methods that you need to implement in order to modify the bytecode. Let's compare them side by side. So this was how the old transform API worked, but now it's a little bit different. So you have basically 2 parallel tracks running during your build process. The first one is this Gradle task, which transforms your project classes and jars, and then puts them later to the D8 or R8 task. And another track is running using the Gradle's artifact transforms, and this one is running for dependencies, basically for dependency jars. Why this artifact transforms is so cool is because the transform dependencies are actually cached across builds and even projects, as long as inputs are the same. Which means if you if you would use Glide and instrument this in one project, but then you would like to instrument it also on another project, this will be reused from your local cache, which can speed up your build significantly. Let's take a look at some code. So this is basically how the new instrumentation API looks like. And if we compare it to the old transfer API, this is much less code. Notice how there is no incremental stuff. There is no handling of inputs, jars, or classes. There is just 2 methods, basically. Yeah, let's break this down. So the first thing we need to do is we need to extend from this thing called ASM class visitor factory. This comes as part of the Android Gradle plugin API. This factory is a generic one, so here you would need to provide the instrumentation parameters if you want to, but in our case, we don't have any parameters, so we just say none here. Next, so the first method here is to define whether the class is instrumentable or not, given the class data. And the class data looks like this. So it contains the fully qualified class name, the annotations of this class, interfaces, and superclasses. So I would say it contains most of the information that you need to know if you want to figure out whether you want to instrument the class or not. And the second method, yeah, it's called create class visitor. But what is this class visitor? We keep mentioning this for a while already, but we didn't really clarify what's that. This comes from this library called ASM, or ASM in short. And ASM is de facto a go-to solution if you want to modify the Java bytecode. It uses the visitor pattern to parse and modify class bytes. So if you, for instance, ever implemented Kotlin compiler plugin or maybe parsed the abstract syntax tree of Kotlin, this pattern is probably familiar to you. It's well documented and optimized for speed, and it's also used by big players like Kotlin, Gradle, AGP itself, Mockito, or R8. The class visitor might look like this. I mean, these are not all of the methods, but some of them. So it basically contains functions for every class member. Like, for instance, visit method would return a method, so another visitor here, and the method visitor could look like this. Again, it contains functions for every method member, like a parameter or annotation on the method or local variable and so on. Asm also has the tree package, which uses essentially a tree structure for bytecode instructions instead of visitors. Why is it useful? It's useful for partial analysis of your bytecode. So, for example, it allows to look ahead or behind for instructions and analyze them. Now, we almost have everything to start instrumenting the bytecode. But what is JVM bytecode anyway? There is a quick crash course here for bytecode. I'm not an expert by any chance, but I try to put it up nicely here. There are 5 main parts of the JVM bytecode. So the first one being constant pool. It's basically a pool of strings which contains type definitions for methods, variables, and so on. There are local variables. They store intermediate results and method parameters. There is also an operand stack, which is used for essentially operations like arithmetic or control flow and so on. So you can push and pop values from the stack, manipulate them, and store the result back. There are also stack frames. They are created for each method call, and each stack frame contains operand stack and local variables. And finally, there are instructions like method invocations, stack manipulation, arithmetic, control flow, as I mentioned. I put up like a quick, dirty drawing here, so to help us visualize this. So JVM has multiple threads, and each thread here would have a stack of frames. And one frame would correspond exactly to one method. If we take a look at each frame, as I mentioned, it contains local variables. It's also called local variable table. It also contains the operand stack, and the frame can reference to the constant pool to retrieve the types of the methods and variables and so on. And by the way, these are the very same frames that you see in your IDE when you are debugging. Yes, so let's take a look at this simple example. So we have a simple function to calculate, to sum up 2 values and print the result. We can decompile it using the Java P tool, which would show us the contents of the class file. So the first thing is the constant pool here. You can see this is like a list of different strings. You can see the fully qualified names here, like types and so on. The interesting thing about the constant pool is that you can actually, so one entry can reference other entries, and this is composable. So in this case, the number 7 entry references number 5 and 6 and composes into this init signature, which corresponds for the default constructor of the class. Then there is a local variable table. Basically, it has like a slot number for each variable. It contains the name of the variable, the signature. In our case, these are all integers. That's why there is an I signature. And another interesting thing about this is that the 0th slot is always reserved for this, so for the reference to the current class. And I think that's it about the local variable table. The next step is the operand stack. So I try to also visualize it here on the right as we go through the instructions. So at first we would define the constant 1, then we would store it in the local variable A. Same for the local variable B. Here we would actually load the local variable A and push it onto the stack. Same we would do for the variable B. And finally, we would use the iadd instruction here to pop them off the stack, add them, and push the result back. Next up, we want to store this result from the stack into a local variable C. Again, we want to load this onto the stack to later call a printLine method on this variable. And invoke virtual here is used to invoke like regular methods on objects. And also notice how it references like number 23 from the constant pool, which corresponds to this signature, basically, so the printLine signature. Now we're all bytecode experts, right? So let's finally do some bytecode manipulation. So let's remind ourselves about the goal. The goal was to transform this log.d with some tag and message into timber.tag.d. How can we do this with the new API? Yes, so we are back to our class visitor factory. Is instrumentable should still return true here because, as we said, we want to instrument all the classes, and we cannot really identify from the class signature whether it contains the Android log call inside or not. So we actually need to go inside this class to find this instruction. So here we would just return true in this case. And for the second method, we would create a new class. We would call it log2timber class visitor, for example. And it accepts two methods. The first one is the API version. And this is the version of ASM. At the moment, it's at the version 9.3, which supports the latest Java version, which is 19. And basically, whenever there is a new Java release, there will always be a new awesome release to support the new bytecode of the new Java version. And the second parameter is we are passing the next class visitor. Since it's the visitor pattern, we are kind of decorating the previous visitor. So that's why we need to pass it here. Another thing I didn't mention, we actually need to register this class visitor factory. For the purpose of the demo, I just omitted the entire Gradle plugin setup. But let's just assume we have a Gradle plugin. It depends on the Android Gradle plugin. And then we are retrieving this Android components extension. We use this onVariants method to do this for each variant. This is also useful because you can actually do variant filtering here. So you can only apply your transformations for release builds, for example, to not slow down your debug builds. This variant API has this instrumentation block, and there is this transform classes with function where we need to supply the class of our class visitor. So AGP would take care of instantiating the class. And the second parameter is instrumentation scope. It can be one of all or project. In our case, it's all because we said we want to instrument the glide dependency, right? Next up, there is a Lambda block for parameters. Since we said we don't have any parameters for our transform, we just leave it empty. But if you would have some parameters, you would set them here. And the last thing here is an interesting one, actually, because we need to instruct the instrumentation API to compute the frames for us. These are the frames from before. So they actually need to be recomputed whenever we modify the bytecode, because you can insert like new bytecode instructions, you can modify, you can remove some, and for that purpose, we actually need to recompute the frames because they will be invalid for the new bytecode instruction set. Let's take a closer look at this frames computation mode. So as I mentioned, frames have to be recomputed, but also the maximum operand stack sizes have to be recomputed. Why so? Because JVM needs to allocate some memory for the operand stack, so it needs to know upfront the maximum stack size for each operand stack. There are 4 modes for this. The first one is compute frames for all classes. It's very slow. I wouldn't recommend using it because it requires a second pass for each class. There is one which is a bit faster, but still slow. It's called compute frames for instrumented classes. You should use it when you are modifying the method body, the class body. The next one is the compute frames for instrumented methods. This one, the most optimal one, and you should use it when you're modifying the method body. And the last one and the fastest one is called copy frames. This would actually just copy the stack frames from the previous bytecode to the new one. So it would take the old bytecode of the not instrumented class and would copy it to the new one. You can use it when you're adding an annotation or interface, for example, because it does not require recomputing frames. Or if you are feeling adventurous and you want to compute frames and max sizes yourself, but I don't know how to do that, honestly. Yes, so now let's take a look at our class visitor. Since we said we want to instrument the log.d, this is just a method call, which is called in some other method. That's why we need to override here visit method, method, function, whatever. It has 5 parameters here. So the first one is the access of this method, whether it's public, private, or final. The name of the method, the descriptor, which contains parameter and return types of this method, the signature, if there are any generics, and if the method can throw any exception. Inside here, what we do, we are again decorating. So we actually retrieve the method visitor from the parent class, from the parent visitor, and then we pass it to our custom method visitor, which we can call log2timber method visitor. Again here, another method to override, which is called visit method instruction. Why do we need to override this one? Because this is what's called when you're actually invoking a method. So it's invoked on each method call. Again, it has 5 parameters. The first one is opcode, so it's type of the method, whether the method is static, interface, or a regular method. The owner class, the name of the method, again, the descriptor, and if this method belongs to an interface. And here, actually, we can start modifying the bytecode. So we know that log is a static class, so we actually need to check if the current opcode is invoked static. And then we also need to check for the owner. And here we would we would use the fully qualified name of the Android log. Next up, we want to check for the name of the method, because we're instrumenting log.d, like a specific one with 2 string parameters. And that's why we use this descriptor here. At this point, you might be wondering, how do we know all these method signatures and so on? There is a really handy IntelliJ plugin or Android Studio plugin, which is called ASM plugin. And what it does, it basically compiles your current class, and it displays how it would look like if you were to write the ASM code, or basically it displays bytecode in ASM instructions. Yeah, and here finally we can change the log method to the timber method. So to help us visualize this, I put this little stack on the right side. So remember that at this point we are about to call log.d, which means we already have loaded its parameters onto the stack. Why this order? it's because it works in kind of in reverse order. So it's like similar to reverse Polish notation. Since the last or the second parameter of logd is message, it will be actually the first one on the stack. And similar with the tag, since it's the first parameter, it will be second on the stack. Yes, so now we are modifying the bytecode. So the first instruction will be swap. Why do we need to swap it? It's because Timber uses different approach, kind of. So it has a static method for tag. And that's why the tag actually has to be on top of the stack, because we firstly call timber.tag. How do we call it? We just define the opcode. We know it's, again, a static method, so we use invoke static here. We provide the fully qualified class name for Timber. We provide the name of the method. And finally, the descriptor. Notice how in the descriptor, the return type here is actually Timber tree, which means when we call this method, the tree will be pushed on top of the stack. And that's why we, again, need to swap the topmost two values on the stack, because the timber.tree.d accepts message as the first parameter, so the message has to be on top of the stack again. How do we call it? Again, we use actually invoke virtual here, because it's not a static method already, but a class member, like a method of the class of an object. Again, we need to provide the fully qualified class name, the name of the method, and the description. And so if we visualize this, the message will be popped off the stack to be used as the parameter. And finally, the tree will be also popped off the stack to be used as like an object on which we call this method. Yes, so that's basically it. So now our log.d is actually already timber.tag.d, and the stack looks empty, but I mean there can be of course more values on the stack, but it looks the same as we would never modify this bytecode. The last step, we actually need to return here inside the if check, because so yeah, because we already implemented our instructions and our log should be replaced by Timber. But in case any of the conditions above have not been met, we just delegate this to the next visitor. So, which means no changes from our transformations, and it will be just delegated to the next visitor without any changes from our side. Yes, also important to remember that we just instrumented this specific D call with this specific two string parameters, but we know that log contains different methods for warning, info, and so on. And also there are different overloads, so if you want to implement this in your own app, you have to account for that. How can we test this? So there are three main approaches to this, I would say. The first one is unit testing with Awesome. So Awesome provides like this thing called check class adapter. And what it can do, it can check if your modified bytecode passes the JVM verifier. Also can check if the control flows are not broken and so on. You can actually unit test this using plain text. In theory, you could just dump the bytecode of a class before it was instrumented, dump it after it was instrumented, and then compare that the necessary instructions were inserted into the right place. And the third approach is to test it, like integration testing with Gradle. So you can set up some sample project, use Gradle APIs to test it, include some other plugins that are using instrumentation API, run release builds to verify how it works with array, and so on. Some tips and gotchas I got along the way. The first one is regarding the Gradle artifact transforms cache. Since the dependencies are cached between builds and projects, this means if you are developing your transformation right now, for dependencies, they will be cached basically. So if you are not finished with your transformation, like you are in the process of developing it, next time you will run the Gradle build, it will not run your transformation for dependencies because they are cached. For that purpose, I found this useful to kind of define a dummy parameter here in your class visitor factory. You should annotate this with like as a proper Gradle input, and later on you can supply like some value which changes over time. Basically, in this case, it's current system time, so it always invalidates your build and always runs the transforms for dependencies. And you can also kind of hide this behind some Boolean flag, so it can be controlled from the Gradle DSL conveniently. Next thing is, basically array runs through all instructions, even those that are there for debugging purposes. There are some instructions that are only supposed to be for debugging, like, for example, line numbers. Array will run through them, which means basically always test your bytecode with array, because you might find some unexpected methods to be called, and then your bytecode is messed up completely, and the Gradle build is failing. The next one is, again, ASM IntelliJ plugin. So it helps you figure out what bytecode to write and what it all looks like. It looks like this, and it's also capable of showing the plain bytecode. So there are multiple tabs here. Pretty handy. I used it all the time. And the last thing here is the JDEX decompiler to see your generated bytecode as source code. It's also very handy because it has full text search, so you can actually search for the things you try to instrument and see how they can look, could look like a source code. Other examples of such plugins, or like who are using this instrumentation API, my company where I work, Sentry Android Gradle plugin. So we're instrumenting a lot of stuff there, like room database queries, file I/O, OKHTTP or retrofit queries. Everything is done for you automatically. So there is a lot of like different bytecode stuff going on. So if you want to check this out, this is a great source, I think. Another user of this API is Firebase Performance plugin. Unfortunately, it's closed source. But if you're using decompilers like me, you can see their sources. They are using it for instrumenting network requests and annotated methods. Dagger Hilt also uses this API to transform Android entry points to extend Hilt classes. And your plugin also can be here. And I want to say that this API is really easy to consume, actually. Just really 2 methods to start modifying the bytecode. I mean, the learning curve is hard, I think, but once you get there, I think it's easier to write. So go write your plugins and share with the community. And with that, I'd like to thank you.